Welcome back. Last time we had to look at some data types, more specifically some more examples on how the data can be stored. We had to look at ways to store negative values while still using the same logic that would only apply to purely positive values. And we had to look at how decimals are stored within C# by using basically scientific notation, but just for binary numbers. And I gave you for the first time some homework, which is what we're gonna start with today. Your homework was to take the two values a and b that I provided and cube them, raise them to the power of 3, and store the result in ac and bc, a cubed and b cubed. And admittedly, there was a bit of a trap here that I was hoping you would fall into. I don't know if you did. The idea was that you would actually use the logic that I demonstrated right before the end of the lesson, for example, by creating a loop that would repeatedly multiply a and b into ac and bc to create a cube value, since we don't have an operator that can directly cube a value. And the trap was that that was actually not necessary at all. Sometimes, when you program, the simplest solution is the best one. So, in this case, the goal was to specifically raise it to the power of 3, which is just like this. If we write it as a program, let's write it down here. AC, we assign the value, that is the combination of A multiplied by A multiplied by A. And BC is equal to B multiplied by B multiplied by B. While you could absolutely use a loop and then have a specific variable that you maybe initialize with a 3 and then have the loop repeatedly multiply the values, cubing is just two multiplication operations. It's pretty simple, pretty straightforward. There was never a need to make anything complicated. This is already the solution to the homework. If you did create a loop, well, that's good, because that makes the next homework easier, because that's gonna be involved in today's homework, where you make the more complex version of this. Anyway, to the topic of today. This is what we had last time. Oh yeah, casting is also something we had to look at. We're gonna look at more data structures. Not data structures, data control statements, control structures. Two of which you've already seen. One was the if, which was just if, then a condition, then run the code block. Maybe I should at least attempt to make them look nice like this. Some instructions like that. And the while, which looked very similar. While condition. That bracket is not a C. Condition. Also instructions. Only in this case we can jump into the code, or we can jump to the end of the code block, and here we can jump to the end of the code block or into the code, and then the code block will jump back to the top. For each of these, we're going to look at more variations of them. This is just a simple branching. A simple, hey, we can skip certain parts of code, but we're always going downwards. This is always going down. This is a loop. This is where we can go down and back up. So we can go down and go back up. And we're going to look at more examples for each of these categories. But before we do so, we should have a look at a specific feature that I did not go into so far, which is relevant for these as well. For that, let me write some code out. int, let's get a space here. A equals 1. Int B was declared. And then we're gonna do this. And like that. Then we're going to do this. And then we're going to set like this. Nonsensical program, doesn't really do anything useful. It's just to demonstrate a certain feature. If I were to try to execute this with our usual logic, let's make a quick table again. So type name value. Just a quick dirty and crooked table. So we first had this instruction, which would declare an A and initialize it with a value of 1. So we have an int A with a value of 1. Next instruction was only a declaration of an integer type variable named B. So no value here. And then we have these curly brackets here, which you already know from our condition here for the if and our while. For these control flow structures, where we signified the code block. If we had several instructions, we had to put them into these curly brackets, so all of them would be either executed or not executed, instead of just a single instruction. What I did not tell you is that you can just freely create these code blocks wherever you want in your code. They don't have to be attached to anything. They don't have to belong to an if or a while or anything else. They can just be freely put in your code, and it's perfectly fine. In fact, we could even put another set of curly brackets in here. I mean, if we were to write that down, I should actually indent that a bit further and put that on separate lines to make it clearer, but you can create code blocks wherever you want. You can group up any instruction you want, and the program will still work. But these do have consequences beyond just grouping instructions for something like an if or a while. Consequences which apply to if and while as well, but we didn't notice them so far. When I now run into this instruction down here, where I declare a C and initialize it with a value, I cannot add this to this table. I have to actually make a separate table now. Well, not entirely separate, it's like an extension of this one. Like, let me actually indent this a bit. Get it a bit to the right. This. It's the same structure, type name value. And now I have to add the C in here, which is int C. We're gonna skip the little details in the future, like this is a simple instruction. This is gonna take A, add 1, and that's gonna be a 2, which is the initial value for C. And then we get this operation B, which is combining C and 2 in addition, and stores it in B. Well, what we have to do now is we look for, well, first we can make the operation C plus 2, which is still the same as always. We take the C from our table, we add 2 to 2, and we get a 4. And we have to store this value in B. Now when we look for B, we first look in this secondary table we wrote in. We've indented it here because it's a new code block, and we don't find a B here. So we look in the next table one up. And here we find a B. And this b now gets set to a 4. And now when we leave this code block here and go to this instruction, what happens is that this entire table is deleted. Like, all of it is gone. C doesn't exist anymore. Now when we use the variables a and b, we only look in this original table. So b minus 1, well, b minus 1 is 3, and we assign that to a, so this is now a 3. If I were to write something like this, the computer would give me an error. This is not valid, because if I look in our table, there's only a and b. C only existed in this short part of our code. Only these 2 lines. This is where C exists. Down here, there is no C. Can't run this code. A code block is not just grouping instructions together. It's also limiting the scope where variables exist. And this applies to the if and the while as well. The curly brackets here are exactly the same mechanic. We still have these curly brackets indicating a code block, a grouping of instructions, and it will still limit the lifetime of a variable. So if I have an if here, if a greater 0, for example, like this, if I make this an if statement, same logic. The code would execute exactly the same way. I mean, in this case, a is greater than 0, so this code block would execute and it would still use the same logic. When we run into this line, it would still have the secondary table, and C would only be added to this table. And then once the if is completed, the table would get read it and C doesn't exist anymore. And of course, if this condition would have been false, this was less than 0, C would never have been created in the first place. There would never have been this second table. So C doesn't exist, but this is fine. We can absolutely change variables that are not immediately part of the scope, but we can always see the scope above, the next outermost scope, or scopes, in fact, plural. Because no matter how many scopes I add, how many new code blocks I make, I can always go back up and look in the next higher table to see if I find my variables there, and I can change them. That also means the same rules for variables exist. I created an int a in here, in this first line, which is part of our first major scope here. I can't create a new variable a in here, because when I try this, well, the computer notices there is already a variable named a. The name is reserved, we can't create a new one. Doesn't work. However, the C only exists in a table that is deleted. So what I can do is create a new code block here. Actually, let's not even make it an int, let's make it another data type. Float C equals B. This would be fine. We still have the same name, we still have the variable C, and we declared it twice in our program. Exists twice. And not only is it using the same name for a new variable, it's even using a different type. So it doesn't make any sense to mix these two, but it would be perfectly fine to write this code. The computer knows exactly this C is only going to be available in this code block. The C here can only be this one. Because once I leave this code block, the C doesn't exist anymore. Once I go into this code block, the computer knows C refers to this code block. And this C is only in this code block. That way you can reuse the name for a variable multiple times in their code. And the advantage for a computer for things like this is that this C only needs space in memory while we execute this code, these two lines, these two instructions, we don't need the space beforehand. Let's remove this if. Up to here, we don't need space for the C variable in our memory. And once we hit this curly bracket and go to this instruction, we can free the memory that was used for C. Memory management itself is a larger topic. We will get into a bit more next time. But simplification is, it makes it easier for the computer to manage the memory. We can be more efficient. We only use memory when we actually require it. And you as a programmer, you can reuse names, which is not exactly the best idea, but there are cases where it makes sense. So you can always use curly brackets to create a new code block. Whenever you use these curly brackets, you define a new scope. You always have this, basically a new table for variables that is layered on top of the existing tables. And this other table, the secondary table, third table, fourth table, always gets deleted once you leave the scope. This is important for you to know. You don't really use this often without any structure like an if, for example. I mean, sometimes you do use it. If you have, for example, a very large, at least that's the only case I ever used it as a standalone feature, a very large function that doesn't make sense to split it apart further. This is going a bit above what we learned so far, but just for those that already have the knowledge, large function, we have a lot of code, and I want to make sure the different parts in that function don't influence one another, which is kind of a weird statement to make. That doesn't make actually any sense to you right now, probably. Either because you don't know what function is, or because you know what functions is, and you wonder why I don't split them up if you don't want the code to influence one another. Well, maybe I'm talking out of my ass today. Let's just say I basically never use this, but you can use it. And it's important that you understand this for things like these special structures. Let's get to if a bit more in depth. So if I have an int a, this one, I can make the condition a greater 0, and then I have, no, plus plus, then I increase it by 1. Actually, let's make it the other way. Let's make it a minus minus, and let's close it up again. So if a is greater than 0, I swear I can draw these. I can draw these. Let's leave it like that. Then we decrease it. Let's say I want another operation in case it is not greater than 0. If it is equal to 0 or less than 0. I can make another if. That would be one option. A less than or equal to 0. But now I have the issue that this operation might have executed. If I look at a here, it might be not the original value of a from on top here. It might be the value of a after it was decremented in here. So instead, I use the keyword else, and I think we already discussed that. I'm not too sure anymore, I haven't checked. But I think I mentioned that. Else is a way to extend an if with a second code block that would trigger when the condition is false. So this is condition true, and this is for false. And then maybe let's make it the other way around. We increase it if it's less than or equal to 0. So this is effectively a is less than 0 or equal to 0. It's always exactly the opposite. You don't have to make a new condition. If that is true, this is this is going to be executed. If it's false, this is going to be executed. So it can only either be this code block or this code block. It can never be both. And it can never be neither. Exactly one of these two code blocks will get executed, depending on this condition. And now let's say I wanted another option. What if I wanted to react to a being greater than 0, and another one if it's less than 0, and a third one when it's exactly 0? Well, things get a bit more involved. What I can do here is, if it's greater than 0, I just do the decrement. But if it's less than or equal to 0, I have this code block here, and in this code block I can create a new if. If a is less than 0, for example, then I can make a plus plus, an increment, and write another else. And in this case, what do you do if a is exactly 0? Then let's say a equals 1. I mean, okay, the code doesn't make any sense once more, but the logic still applies. So this code is when a greater 0. This entire code applies only if a is less than 0 or, let's write it down in words, or a equals 0. By the way, we should maybe quickly talk about this. This is the operation you would use to identify if a value is exactly another value. So based on these two, you would assume maybe that a equals 0 is a condition. Is a equal to 0? But based on everything you've seen so far, you know that this is actually an assignment operation. This would assign the value of 0 to a and then return the value of a, the new one. So as a condition, this wouldn't work, because if I write if a equals 0, like so, well, it would assign the value of 0 to a and then return a 0, and 0 is an integer value, but we need a boolean, we need a true or false. 0 is not true or false, not in the meta way, not in the higher level language C# way. Down in the computer, in the memory, it will probably be exactly the same value as false, but we are strongly typed, it needs to be the wrong data type even if the bits match exactly. So this does not work. If we want to compare it, we need to actually use a different operator, which is 2 equal signs, which is specifically to let us know that we want to compare the value. If it's equal, whoop, that was my pen. If it's equal, return a true, and if it's not equal, evaluate this to false. You can think of it similar to the double and double or, which was specifically for Boolean, for true and false, while the singular and or had actual effect on integer values as well, because they were bit operations. So when you use Booleans, think of 2 operators. Well, this was greater than 0. Well, actually, don't think of 2 operations for these greater and less than signs, because greater or less, these double combinations are also operators, but here it's exactly the other way around. The simple single operator, that's a Boolean, and these doubles actually create integers, for example, because they're also bit operations. So sometimes C# is just weird. Anyway, this is the entire block, and this one is specifically then for the case where a is less than 0. And this one specifically for a equal to 0. Like we know a, if we are in this block here, we know that a cannot be greater than 0. And if it's not less than 0, and we hit this block here, we know it has to be less than or equal to 0, and it's not less than 0, so it has to be equal to 0. And if we look back at what we discussed last time, this if block, or this if here, is one code block. And so is this if, including the else, because the else is directly attached to an if. You cannot have a standalone else. It's always attached to an if. So if you just had this code, this would be a code block that you could write, for example, in a while. And the entire if would be assigned to that while, because it expects a code block following. And the same way, if we have an else attached to the if, well, this entire if-else structure here would be recognized as one large code block. So if I just have a while without any brackets, it will still recognize this entire block as belonging to that while. And the same if I have an if. The entire block here would be assigned to if this condition for the if is true, even without any curly brackets. And this means on the small scale, we can actually skip these two curly brackets, because this is also one large code block, an if-else combination. So this else will recognize this complete structure, this if-else here, as belonging to itself. We can leave the curly brackets. And usually, when you write a program, you don't even indent it anymore, because this is also pretty common to see, that you have an if, but you have further conditions for the else. So you put it in one line. So let's move it up here. We will put it in the same line, if, and then a less than 0. Then we put curly brackets here again, a plus plus, and then the else. It's exactly the same code as before. Just rearranged a bit. Just basically, we just hit backspace on this line and move the else and the next if in one line. Now we have an if, and an else if, and an else. If, else if, else. And we can extend this further. I mean, it doesn't make sense much here, but what if we, instead of making this a condition, what if we use the comparison? Okay, I'm not writing this out fully, but maybe this is that, and maybe we wanted 2, and then maybe we wanted another one here with a equals 3, this, and then maybe another one, else if a equals 4, sign -1, and then optionally maybe we still want an else. No matter if it makes sense or not. So we have a structure of if, else if, else if, else if, and else. So every time we have a code block, we have one, or let's use, we have an A, we have B, C, D, E. Each of these code blocks has a specific condition assigned to it. this code block A can only be called when A is equal to 1. And if that's not true, then we further continue if A equals 2. And if it's not the case, we further continue with A equals 3, A equals 4. And finally we say if none of the others were true, if none of them applied, we just go to code block E. We know that at least one of these will be executed, exactly one. And depending on the value of A, it's going to be one of these 4 code blocks here. And if the conditions aren't as simple, you might actually have to think about it a bit, because now they influence one another. For example, for code block C, well, what do we know? This code block C, if it's executed, it must be because this statement was false, and this statement was false, and this statement was true. If it's not a straightforward A equals 3, but more of a deduction of is A greater than 1, is A greater than 2, is A greater than 3, for example. Let's actually work that out. And you don't really know what the value is, but you can make some statements about it. You have to keep that in mind. Large group of else ifs means that the further you progress down, the more complex the condition will get. Down to the last else, if there is one. Keep in mind, this is optional, this might not exist. But if it does exist, it will be if none of the other conditions applied, which is still potentially a complex condition itself, even though you don't have to write it out anymore. Also, the computer will have a lot to do to reach this last code block E, for example, because it has to first check if it's this code block, or is it this one, or this one, or this one. No, then it must be this one. There's a lot of work. These 4 code blocks, checking every condition, just to get down to here. Sometimes that's necessary. If you have a complex condition, if you have a complex series of conditions that might not even test the same thing, but completely different variables that are somehow interconnected in some way that only you as a programmer know, well, yeah, you might need to do this. But going back to our first example of just checking for is it exactly this value, well, there is another data structure that does the same thing, but it does it in a more efficient way. Let's put it that way. Both for you as a programmer, it's more efficient to write and read, and for the computer, it's more efficient to compute. Let's try to write the program again, but with the new structure. Let's see. We start off with the int a equals 1, just to have the variable with the default value. And now the structure. The structure is called a switch. And so we start writing that out. Switch. And similar to the others you've seen so far, we start with the name, and then we add normal brackets. And this time we don't put in a condition, we put in a value. So our A right now. Because we want to switch between different branches of code depending on this value. Think of it like a railway. Our code goes here, or maybe it goes down here, maybe it goes down here, or maybe it goes down here, or maybe here. So A, B, C, D, E. So we have 5 different branches of our code, 5 different ways we can go from up here to down here. And if you imagine these are rail lines, then each of these is a potential switch we're going to turn on. If you switch it, how do you call it? Ah, darn it. I know the German word, but what's the English term for these? Ray split? Not crossing splitter. Switch. Track switch. Oh well, whatever. At each of these points, we could switch to go further down or go to the side. Decide which way we want to go. And this is a more comprehensive structure that does exactly that. We can split our code flow into different branches depending on this value. This is just straight up a variable that tells us which of these is gonna flip in which direction. And the interior, then of course another curly bracket. This time I'm not closing it up because I'm not sure how far I will go now. And then each of these points here, each of these potential branches is called a case. Because whenever we hit this, it could be the first case, we hit A, or another case where A is 2, where we go to B, and in case it is 3, we go to C, in case it is 4, we go to D. And that's actually the keyword, case. And then this is where the structure starts to break apart a bit from the norm that you're used to. It's kind of weird. We now put in the exact value you want to compare it to, like a 1, and then add a colon. It's one of the weird structures in C#. It has a couple of other weird quirks. Like switch is strange, but it's so useful. It's one of the most useful control structures you will learn. We're not even going in depth with the full scale of what it can do. We're only looking at the simple case today. So first we had the case where it's exactly 1, where A is 1, we hit A minus minus. So and this is what happens here. We check if A is exactly 1. A equals 1. And then we decremented A. Like that. As you can see, no curly brackets. They're not necessary here. What is necessary, however, is to make sure that this case has an end. We need to somehow tell the system that case 1 starts here. That's where we defined it. This first case for the value 1 starts here. Just like curly brackets usually start a code block. We don't use curly brackets here, so we need some other way to tell the system, hey, this is the last instruction. After this case is over. Do something else. Now, you might assume that I just write the next case, which would actually be written like this. And now the computer knows, hey, this is the next case. Our entire code block is between this case and the next one. So this is the only instruction. That's not how C# does it. There's another special keyword that we'll have to learn. The third one for the switch statement, which is called break. Which sounds a lot more ominous than it is. Break simply tells us that, or tells the computer that at this point, stop, continue somewhere else. Like wherever you are in the logic, whatever control flow you're in, whatever code block you're in, you're done. Abort. Stop processing it here. Go to the next. And this is how we declare, or tell the computer that this is the case that we start for when A equals 1, which is going to have this one instruction, and this is where it's going to end. Well, it's less we're telling the computer this is where it's ending. It's more this is actually a command. This is an operation on its own. This one statement is an operation that tells the computer abort currently executing whatever this is. Because we can actually do this. If a... Okay, this is kind of dumb, but... What's 0? which, yeah, it's gonna be 0, we know that, because it was 1 when we hit here, but then we can make it a break. I'm gonna skip the curly brackets, because this is the only instruction. And otherwise, we can make another decrement and then hit the break. So, because we're not using curly brackets here to mark the end of the case, we can actually use the fact that we are in a control statement, like an if, that can switch around which code we're executing. We can make a dynamic closed curly bracket, so to speak. By hitting the break, we know this case is over, but we can run this operation as code, as normal code, and therefore we can determine when it hits. And we can make further branches within this case that use the existing branching logic for this switch. If that makes sense to you. So we could do that without this break. We could make it a bit more involved. But this is a way to just simply use the structures that we have a bit more efficiently. Though it can be annoying too at some time. In some cases, because our actual code just had this one instruction and then we still had to add this break, which the computer will check for, by the way. You have to add a break somewhere in your case. No matter which branch we go down, in this case, we will have to have some point at which a break is called. If we don't have a break, if there's any branch in this case that could be hit that doesn't have a break, the computer complains and we will not be able to run the program. So for something like this, where it's only a simple statement, that's annoying, but it has to be this way. Let's do the second one, 2. And 2 was A++, A++, and we have to hit another break. And then case 3. Case 3 was A equals 1. And another break. We have to write them out every single time. Which is what I meant when I said annoying. Nope, wait, not a semicolon, this is just a normal colon. A equals -1. Break. And, well, now we hit the else. Else, in this case, would not apply to a specific value of A. We only know it's less than 1 or more than 4. But basically we know it's not going to be 1, 2, 3, or 4. So any other value that could be stored in an int except these 4. And for switch, there's also this else. And here it's called default. It's like a case, but with a special name. It's like, if none of the other cases applied, then use this case. And what did we do here? We set A to 0. And we still need to break. And now we can close it off. So let's clean it up. Should probably use the tools I have instead of making that manually, but it feels nice. I like working with a pen. But we're gonna use the tool here. Copy that over. So, like this. Maybe not the best example, because now the code is actually longer. But imagine that there's more going on in these blocks than just one simple instruction. In that case, it might actually be easier to read. Also, with a switch, you as a programmer know immediately what's going on. You know immediately, we're gonna check the value of A, and depending on the specific value, not just any weird conditions, but the specific value, we're gonna execute one of these blocks. Or this last one if none of these values showed up. With an if, else, if, else, if, else, if, else, you have to actually look at the different conditions, because you might assume with the first glance, hey, it's just checking for specific value like a switch, but maybe there's more going on. You can't tell immediately. Also, switches are capable of making it easy for the computer, because now we don't have to actually check if A is 1, and if it's not, we check if it's 2, and if not, we check if it's 3. The computer can make internal logic that just goes directly to the proper case immediately without checking the others. That works because A, comparing it to a number, simple operation, but A is also just an integer that could, in this case, well, tell us the specific case. Well, if A is 1, execute case 1. If A is 2, execute case 2. So the computer can jump directly to the proper case. I should have the pen on. Immediately to the right case, depending on its value. Like, it can use the value of A immediately as part of its operation. Think back to our made-up CPU, where the jump instruction would receive an address. Well, now imagine that I modify that address by adding the value of A to it, or a multiple of that. So maybe I just jump to the target address where the first case is, or maybe I add the value of A to the address and jump to maybe 2 addresses further down, or 4 or 5. Depending on the value of A, we can jump directly to the proper case and execute that code without making any checks for the value, without having any conditions. We don't need to compare the value to anything. It's a bit more complex because not every switch will have it this easy, but there are optimizations you can do. In C# in the background, you will actually have cases where maybe this value is modified because we're not checking for 1, 2, 3, but maybe for 10, 11, 12, like something else. In which case it might just subtract 10 first, and then it will have still the +1 logic. Or maybe it will make larger gaps, and then it will split this in the background into 2 different switches, just to still have the option to directly jump to the code instead of making any checks, checking any conditions. Just performance, man, for the performance. Also, switches can do some more complex stuff, which we can't go into yet because that requires some more background knowledge I will get up to in the next lessons. This is already a simple case, very useful for a lot of things in programming, but also just refinement of something else, with a bit of a twist, and that the logic, it looks a bit weird. Like if you know the rules for the other control structures, C# in general, this is kind of coming out of left field. But we're gonna learn this stuff. And as a last addition to our little family of skipping code, just going downwards, another structure you need to know about for ifs. It's not actually a structure, it's an operation. So if we go back to int a equals 1, let's copy that again. If a greater 0, let's make a simple case just like this. Greater than 0, then a minus minus, else, oh, let's write that out properly, let's take our time, else a plus plus, like this. we can short this. Specifically for the case where, let's say we had a different variable, b, and we didn't want to have a change, but maybe you want to have b set to a, -1, like this, and here we have b equals a +1, so like this. Depending on the value of a, we either set b to a -1 or b +1. This structure where we just want a specific value, but depending on a simple condition, on one condition, not necessarily simple, there's the ternary operation. So instead of this, we can also just write b equals, then we make the condition a greater 0, and then we have question mark. That's the first symbol. Then we followed up with the one assignment we want for that case. A is greater than 0, we want to use a -1. Otherwise, we want to use a +1. This statement. Or we could also rewrite this in a different way. Equals, because both cases use a, we can write it as a plus, then a greater 0, question mark, -1, +1, because this is just the constant value -1. That's why there's minus symbol, and here it's just +1, but we can actually leave out that plus because C# knows that this is already positive. Like this. This is also another way to write this out. What happens is, this operation has 3 parts that are separated by first the question mark and then a colon. And if, when this operation, which is, I think this is the first time you've seen something, yeah. So far operations were always directly in front, a symbol directly in front or after or between the operands. Here we have 2 symbols that are split apart between 3 operands. Yeah, this is one operation. It will first check the condition in front of the question mark on the left, and then it will either use the code block directly to the right of the question mark, or the code block that will follow after these colons. You can also go a bit further. You can write something like, this is not exactly this code. If I move this out, if we look back into the else if case, if a less than 0, a +1, else b equals 0, like that. Now we have the if, and then an else if, and then an else, though I deliberately put the block here as part of the larger else block, because that is more representative of what's going to happen now. We first check if a is greater 0, first condition, and then the question mark to indicate that this is now a condition. Then if that condition is true, we execute this next part after the question mark up to the colon. So we want to assign for a greater than 0, a -1. Then we put down the colon. So this is one block now. This was the condition. And if the condition is false, we're going to execute everything that's following after the colon. Before that was also just a simple statement like a +1. But you can actually make another check. A less than 0, question mark, a +1. and then colon 0, semicolon. Because this operator will look for everything up to the colon, and then everything after the colon to the end of the instruction with a semicolon. So this is another subset. This is also like, this is one condition. Actually, let's make this different. So this is one block, the condition. This is the second block, the case if it's true. And this is one large block, the case if it's false, which itself is one condition, case if it's true, case if it's false. That's the ternary operator. It applies on 3 operands. It's 2 different symbols, which are surrounded by 3 different operands. Also very useful in many cases, because you only want, based on a condition, one of 2 values. In the extreme case, 2 constants, +1, -1. This is maybe a bit weird, again, similar to the switch case, but at least in this case, there's not really a statement. This is not a statement of as much as it is an operation. That's all it is. Just a weird operation, which fits in a single statement, in a single instruction, and can even be used in something like this. So if, make it a bit weird now, use brackets to make clear that what the priority is. If a greater 0, then use 1, else use -1, like this. So there's a ternary operator inside the condition, which is evaluated. So depending on A, we either result in a 1 or in a -1, this entire block, when it's resolved. The computer calculates it, and then we compare that to 0. And then we either compare a 1 or a -1 to 0, which will result in either true or false. Which is effectively the same as just comparing is A greater than 0, but just to show that you could do something like this, which might have uses somewhere for you. Right, that's enough of if. Let's go ahead to loops. In C#, I'm aware of, well, at least in terms of actual statements, of 4 different loops. One you've already seen, which is the while. And let's think of a program that can okay, let's do it this way. Int a equals 3, int b, that, and okay, let's write this program. While a greater 0, b equals b plus a, whatever. Actually, that doesn't make sense. Equals a. Let's do it like that, and then it's a, then a, e. That's a nice program. So, if we execute this program, and want to check what's gonna be in B down here. Well, let's follow the program with the table again. We have first the int a, the value of 3, int b, unknown value, Like again, our little table, I'm not gonna name it anymore. We're gonna check the condition, is a greater than 0? It is. We go in and we set b to a. That, and then we increase a by b. So that's 3, so we're gonna go to 6 now. Then we go back to the top of the loop here, check the condition again, is a greater 0? Yeah, I should have done it the other way around. Anyway, which it is, and then we go to b equals a. So this is now 6. And then we increase a by b, which is now 12. And you can see where this is going. This loop will never stop because a is always greater than 0, except it isn't, because you also know that at some point a will get too big for the integer data type, and we'll get an overflow, where we get to the highest value, or beyond the highest value we can store, and suddenly set the first most significant bit, which is the sign bit here, and the entire number will be negative. At which point this loop will be false. So it's not like it's an endless loop right now, though it could actually end up in one if we are really unlucky with our initial numbers. Special case. Yeah, I made just a mistake when creating this program. It would still stop after not too long actually, because exponential growth. Never mind. Let's reset this and let's write a more sensible program. That and plus. Let's do it like this. We decrease. See, the thing I wanted to demonstrate doesn't work like this, so... I can't think of a really nice short program. That actually makes sense to go for. Yeah, let's just keep it dumb. Doesn't really matter. It will go through 3 times now in the loop, because this time we decrement. We start with an A3. It's true, we set B to A, we decrement A. 2 is greater than 0, we set B to 2, decrement, repeat, repeat, repeat. So we would end up with a B equals 1. Because the last loop, where we set b to 1, so a is 1, we decrement a by 1 to 0, and then this condition would be false and we jump to the end. So in this program, b would end up as 1. What if I have this program though? What will b have in the end? Well, we start the program, we stop the loop. We start at a greater than 0, which is false. Program is done. B doesn't have any value at all, which is not good. It means we can't use B in the coming program here. Can't reliably say that B has a value. So to correct that, we would need to give it a value, and to keep the logic of our loop here intact, even if it doesn't make any sense. That seems to be the theme today. we just set it to A directly. So now B would have also the value 0. However, we need to now run this operation twice. We had to write it up here, and then we had to write it again in the loop here. Imagine this would be a more complex set of operations, maybe several instructions that are combined. Writing that out twice is a bit annoying. So, alternatively, can keep the old program. That's like 8 first is equal 1, and B not equals anything. Just start off without any initialization, just the declaration. And now we still write the loop. B equals A minus minus. But now instead of putting the while up here, we put it down here. However, now the computer doesn't really know that this code block belongs to the while. I mean, you could assume that the computer knows. But the designers for C# decided, no, the computer doesn't know. Or maybe it's better for the human to read that there is another keyword up here, which is do. This is also loop. And another quirk that shouldn't actually be necessary, but apparently is necessary for some reason, is we actually need to add a semicolon here, as if this is an instruction. So while this is entire code block as is, no problem, we have to actually add a do up here to signify the start of the code block. I mean, we didn't need to signify that this is the end of the code block, it was natural, it was obvious. So why does it need to be a do? I don't know. Anyway, we start with the do, then we have our code block, and then we have the while below the brackets. And then we also need to add the semicolon to tell the computer that this is the end of our code block, as if this is an instruction, which is also, again, why? I don't know. It is just what it is. This is the do while loop, which is very similar to the while, only here we check the condition first and then execute our program. Here we execute our program code, then check the condition, and then maybe repeat. So check the condition, execute if it's true, check again. Execute the code, check if the condition is true, repeat if it is. So this program, if A is equal to 1, well, we first set B to 1, decrement A to get to 0, then check the condition. 0 is not greater than 0, and so we go to the end here. We're done. And B would be equal to 1, same as with a while. If we set it to 0 now, we first go into this code, we still assign A to B, so B is now 0. We decrement, get to -1, which is still not greater than 0, program ends. So B equals 0 in this case as well. But we didn't have to write this equals A twice, we only had to write it once. In the same way, if this would have been several lines of code, more complex code, we only have to write this once in the body of the do while loop here, within our code block. That's the big advantage it gives. This one, check the condition first before it makes runs any of its code. This one, the do while, will execute its code once without any checks. And after that, it will behave exactly like the while loop. It checks the conditions, and if it's true, it will execute the block again. So exactly like the while, only it starts by executing the code block once. Guaranteed. Which has its uses. Though I don't use it as often as the while. And to our last loop, really there isn't much more to say about this. That's why I'm stopping here. The last loop is much more common than the do while. Actually, also for me at least, much more common than the while. And it covers a very special case again that you can do with the while. So honestly, we actually kind of did it already here. This exact same program, if we think about what we did, we started off with an a at a specific value, and then we just repeatedly decremented a. So if a was 5, we would start with a 5, and as long as a is greater than 0, we would constantly reduce it by 1. So 5, start at 5, and then we check if 5 is greater than 0, we do some code, and then we decrement by 1, and repeat. And then it's 4 greater than 0, and we repeat. And then 3, repeat, 2, repeat, 1, repeat. We hit 0. We end the loop. So this AE was just constantly counted down. And all the while we count down, we do some things in between with that value. This type of structure will be much more useful when we see some more advanced data structures next time. Or maybe time. Actually, we might discuss arrays next time already. But yeah, there's a special loop because you use this concept a lot, and it's just easier to see and read and write with a special loop we call for. 3 letters. And it also has brackets, of course, but these are a bit more complex. Let's skip this for now. The for also has the curly brackets, where we can write our instructions. Like, I'm just gonna assume we have the end equals 5 as above. Maybe I shouldn't assume, maybe I should write that out as well. Just to be sure. It's 5. Actually, no, the point is that we don't need to write this out anymore, so just the int b is enough. Well, kind of. We'll see in a moment. So b equals a, skip like that, and then we close off the bracket. What are the parts that I've left out compared to the program above? Well, for one, this first assignment. We're gonna ignore that for now. But other than that, we didn't declare a, we didn't initialize a, we don't compare a, and we never decrement a. But these 3 boxes, this is what's left out of our code down here. And these 3 boxes are now going to be put into these brackets here all in once. We start with the int a equals 5. And a is 5, semicolon. Then we continue with the condition a greater 0. Then we add another semicolon though, other than here. And then the a minus minus. And we don't put a semicolon here, we just close the bracket. So we have 3 boxes. We declared and initialized the variable. We have the condition for the loop. And we have the decrement, the change of our variable. This would be a very basic version of a for loop. This is now gonna pretend like we wrote a for a while loop here, in the exact same style as here. The for loop will start by performing the first block once. This is before anything else happens. This first block we add, which is everything before the first semicolon. These 2 are very important. Everything before here will get executed once. Then once it is executed, we will now pretend this is a while loop where this condition is checked. So everything is initialized, we have an a equals 5. Done. Now we check the condition. Is a greater than 0? A is 5. If it's just greater than 0, we execute the loop, which is b equals a, so we set b now to 5. Usually in a loop, we would just go back to the condition. So in here, after the curly bracket is closed, we end the code block. Usually would go back to the is a greater than 0. The for loop, however, we now add this last box, this last segment after the second semicolon, and execute this now. So this was right before the for loop. This is kind of on the last line, like as if it is the last line of our code in the block. So we still decrement a, play 1, and we go back up, check the condition once more. We execute this code. We decrement a, we check the condition again. Assign a to b, decrement a, check the condition. Code, decrement, condition, code, decrement, condition. Until at some point, the decrement will set a to 0. We go to the condition, which is now false. We go to the end of our loop. We're done. So this for loop right now behaves the same as this while up here. We're gonna see some more examples of this. You don't have to really understand it right now. If it's still not clicking, there are some special routes in here as well. For example, this code here can actually be several instructions, but you don't separate them with a semicolon, you separate them with a comma. And again, we will see probably some more instructions, some examples for this at some other point. For now, just remember that we have the while loop, which has a special case for running the code once, which is the do while, which might not be used that often, but it is very useful to shorten the amount of code you have to write. And we have the for loop, which covers a very special case that still has a lot of code you have to write out, but as a programmer, writing this out in one line because it all belongs together is very simple, very quick. And if you read this code, the moment you see for, you immediately know, okay, someone is counting up or down. Could also be down, could also be up, could also be something completely different. Then examples some other time. Just remember this exists. For loop is a special while loop. The exact same code, just written slightly different. You can always just use a while loop. Same with a do while. You don't need to know the do while, strictly speaking, because you can just copy the code and recreate the same behavior. Of course, because this is now the exact same as the old while, this b might never be initialized. If a initialized as 0, then this condition would start off with false, and we never hit this code, and b would not be initialized. So in this case, we do actually have to manually write this, which is the difference to the code above, because here we actually had the a already. We could just use a. Down here, the a is initialized within the loop, in the header of the loop here, not up here already where we have the b. So we have to manually add the 0. You could, however, delete this part. It's perfectly valid code. You just have to leave the semicolon, but you can leave the space in front completely empty. That's fine. And then we write the int a up here. This is fine. You can do this. In the same way, we can also skip this last part here and write that down here. This is perfectly valid code. The same logic still applies. When the loop starts, when this for is executed, or started, we first execute this block here, which contains nothing, so nothing is done. Nothing happens. Then we check the condition, which in this case is false, so we skip to the end. If we set this back to the 5, condition would be true, and we execute this code and this code. And then before we jump to the top and check the condition again, we execute this code here to make the decrement, or whatever is written in here, which, well, there is nothing, so we don't do anything and just check the condition again. So right now, this for loop here is identical to a while loop. So a for loop where you leave the first part empty, just put a semicolon, and then after the condition put another semicolon and leave everything to the end of the bracket empty. This is exactly a while loop. Exactly the same. But we can just move this out, put it up here. And we can put the a equals 5, can put that in here. We could. And that's a for loop. There's a fourth loop we're not going to get into today, which is kind of a very special version of the for. Because this counting down or up is used in a very specific scenario, and because this scenario is so common, this code structure is used so commonly, which is why for loops are used so commonly, and for loops can do actually some weirder stuff. So instead of just going minus minus, I might decide I want to decrement by 2, not just by 1. But there's a special loop that is kind of focused on decrementing by 1 or incrementing. We'll get to that at some point. Maybe not next time, maybe the time after that? Probably. Next time is going to be full already. Any case, those are loops. Let's keep in mind the while loop is sufficient for everything. You can do everything with a while. No problem. It's just useful to know that the other loops exist and you will at some point start to use them. As far as conditions go, well, we have the switch case, which is a special version. Please scroll back. I told you to scroll back. Thank you. We have the switch with the cases, which is a special version of the if-else. Or if, else if, else if, else if. Which can be useful, but it's also okay if you just go for else if, at least for a simple program. If you just know if, else if, else if, else if, that's fine. And the ternary operation, what is it? Okay, some of the input is, I don't know which update it was, but some of the last updates have made gestures really, really bad. Like seriously. That used to be like, bam, it worked, done, instant. And now I have to make several attempts for it to recognize my gestures. But I got a ton of new features that I don't care about. Software development. If you don't do it yourself. Ternary operation. Very special case of the if-else, else-if logic, which can be put into a simple operation instead of larger statement. But again, you can do it with an if-else. So a simple if-else and a while are all you need to write code. Everything else is just bonus, because it makes your life a bit easier. You don't have to know it. If you want to pursue a career in programming or do larger projects, you should have a look at them. At the very least to read other code, but no pressure there. Now, let's go to your homework for this time. As promised, it's going to be a bit more involved. And you might want to make use of some of our structures. The code structures I showed you today. Maybe not, you don't have to. You could. So last time I gave you an int a Let's leave that open for now. And an int b. And you were supposed to create an a cubed and b cubed, which was pretty simple. Now, today we're making very special one. Let's split this out into... No, int b was right, just no initialization, just declaration. And let's say... Let's make a simple example. So your goal will be, or well, basically you get an X homework. Homework. For a given... God, I haven't used real math in so long. You can see it, I'm doing quotation marks, real math. For a given x, where x is equal to a squared not find, calculate x to the power of a. So for this example here, for our 81, calculate a. A is integer with a, was it element of n? Like, I think that was the way you read it out, right? The set of all natural numbers excluding 0. Element of the... I think that was it. Wait, I had n, was it 0 here or there? If I include 0 and z for all integers. But yeah, you can... A is gonna be an integer, a positive one. You can exclude 0 and all negative integers, so 81 for example, 81, x 81, e equals 9, a equals 9, because plus equal to 9 squared, 9, and then you're supposed to calculate 81 to the power of 9, which, whatever. So this is what you're supposed to do. Let that thing sink in for a moment. I'll be honest, this might seem complex at first, but it's actually very easy. Well, easy enough to understand. You will have to write some code. Again, this time we have a squared, which is something new. The x to the power of a, that's something you had to do for the last homework, only this time it's not set to an a equals 3. You don't have to just cube it, you have to live with very different values. Again, a is always a positive integer, so you always have at least 1 there. You don't have to worry about to the power of 0 or about negatives. You still have to calculate it. And to calculate the, well, basically what you have to do here is make the square root, so this is the same as, and x to the power of a, which is equal to 2 which is equivalent, maybe like that. you have to calculate the square root, which is something new, but it's actually not that hard. You already know how to very easily calculate the square of a number, which is a multiplied by itself, right? A squared is just a times a. And if you want to find a square root, there is no reason for you to actually calculate it in a complicated way. You have a computer to do computing for you. We know a is gonna be a natural number, and especially data type int. Actually, I should maybe rewrite this. X. Calculate y. Y. Where y equals x of a, which is equal to x to the power of its own square root. Like that. Maybe like that. And y. That's better. We know there are only going to be a limited number of values a can be. And you could just try them all one by one, square them, and see if they match up to your x. Just as a hint, there are more efficient ways to do this, there are less efficient ways to do this, but calculating the square root of an integer is really simple. You just have to find a way to do it once. And once you've seen it once, it becomes trivial. And then you have to, of course, raise a value to a variable power, which you can do now with repeated multiplication. Which is also something you already know how to do, because you know how to do repeated addition to create multiplication. I think that's all I'm gonna say to this. I believe I actually wrote this almost correctly down here. I hope. Math nerds, or actual mathematicians watching this. Why would a mathematician watching this? If you're into math, you already know programming. Whatever. Please correct me on this. Anyway, see you next time.